Okay, so can I start please? Just a small thing or just a small modification to Ampere's law. So what does Ampere's law tell us? If you have current, how do you find a magnetic field due to a current? So if you have a wire, and in a wire, if I consider that I have a current which is flowing in a wire, so I can assume that I have current density inside the wire. So these are all the current density vectors which are flowing inside the wire. So if I want to find the magnetic field at a distance, let's say r from the center, at a certain point, let's say q or whatever the point is, then what I do, I make a circular loop around that point, and then I set a line integral along that loop. That loop I would call P, and if I do this integral, on the right hand side what I get is mu naught into the I enclosed. And what is this I enclosed? It is the current which passes through this surface S. Up, you have current we previously described as current equals to J dot A, but that would be the case अगर आपके पास पूरी एरिया के ऊपर करंट डेंसिटी कांस्टेंट हो. But what you have is you have this surface, यहाँ पे करंट डेंसिटी है, साइड पे नहीं है. You have to set up an integral like this instead of just writing it in that way. ठीक? And when you do this integral, what would you get? You would get the total current which is passing through it. और total current क्या होगा आपके पास? There would be not the total area, but just this area. This cross sectional area multiplied by J, that would give you the total current. So if you remember, we did an integral this morning. जिसका हमारे पास क्या था? Get a solenoid जिसका we have a solenoid of area A, but we have a wire जिसके ऊपर हम EMF फाइंड करना चाह रहे थे. So we did an integral over the whole surface, लेकिन क्योंकि B हमारे पास सिर्फ यहाँ पे था, so you only multiply this area and not the total area. Exactly the same. So that's a modified form of Ampere's law, just to make things the expression complete. Some people are getting confused कि मैं ये पूरा area क्यों नहीं ले रहा हूँ, क्यों ले रहा हूँ. So that's the reason. अच्छा. So now coming back to Faraday's law. So what did we say until now? That Faraday's law is something which gives you non-Coulombic electric field. But this is not all what it gives. It gives something else as well, and it also explains some other phenomenon rather than non-Coulombic electric field. And how does this do that? For example, what does Faraday's law tell me? That the induced EMF, which you induced in a certain path or a certain current or a certain circuit element, it is given by the derivative of the flux. And by flux I mean magnetic flux. So imagine you have an area which has an area vector A, and you have a magnetic field which is at a certain, let's say, slight tilted with respect to this area A. What would be the flux through this area if this whole magnetic field is uniform through it? So if you look at the cross section, you have at the cross section of this, you have this area which is in this direction, and you have the V vector which is in that direction. So the V vector would have two components. One component which would be V perpendicular, which would be perpendicular to this surface, and then another one which would be V parallel. So flux क्या होएगा आपके पास? Magnetic flux है, that is given by V dot A, and if you do this integral, what do you get is B A cos theta, where theta would be this angle, or you can write it as B का perpendicular part multiplied by A. ठीक है? Makes sense? So this is what you have. Let's try to find out what the EMF is. So then the EMF is minus d by dt into B perpendicular, and by perpendicular mean the component of V which is perpendicular to a certain area A multiplied by A, and here I am assuming that the total magnetic field is uniform over the whole area A. So I can write it in this expression.
Could you explain the significance of the negative sign with delta?
So the negative sign, I've said that it gives you the direction of the EMF which is produced as a result of the changing magnetic field, which obeys Lenz's law, and this negative directions basically give you the direction of minus d dt that we have done 2 or 3 times. So if you have this derivative, you have two quantities in there. So if you open this up, what you get is minus B perpendicular d by dt of area minus area multiplied by dt of B perpendicular. So EMF, you can have EMF produced due to two reasons. One is if your area is changing through which the current would flow, or the magnetic field is changing through which the current would flow. So until now we have only discussed in the context of Ampere law those cases जहाँ पे आपके पास magnetic field change हो रहा है. For example, this morning we were taking the case अगर आपके पास a magnet है and you have a loop, a small conducting loop. What happens if you bring it closer to that loop or move it away? आप basically जो magnetic field है इसका, it is either decreasing or increasing. So the magnetic field component, which is perpendicular to this area A, which is enclosed by the loop, is either increasing or decreasing. So what you are changing by moving it is basically this thing. When you move it, your B का perpendicular component, and let's say, so this is of course B. This is B here, but B का perpendicular component ये होएगा, इस B का perpendicular component ये होएगा. So all those components. So when you move this closer, this component increases. If you move it away, this component decreases. So what you are doing is by moving this thing is changing this B component, और जो EMF produce होता है आपके पास इस loop के अंदर वो इस term की वजह से होता है. Why we don't have this thing? This term includes the change in area per unit time, and because the area inside the loop is not changing, so this term would give you 0. Okay? So what the point is that you can have an induced EMF due to the that those two ends are connected by a resistor R, and if you put another conductor on top of it, which has this length L, and what you do is if you pull this conductor with a certain force and move it with a constant velocity, this we call as the bar velocity, V bar. So this is a metallic bar which is placed on top of this place, so you can move on top of this, and you are moving it along the axis. So let's say this distance is x and this distance is L. What you are doing there? You are placing this whole thing in an external magnetic field. That's what we said. Let's say that field is into the board, and that field is constant and it's not changing. So the magnetic field, so what you have is you have a loop here. और loop कहाँ पे है? You have this conductor on top of these two conductors, and those two conductors are connected by another conductor by a resistor. So you have a loop which is defined by this path. So you can have a certain path through which current can flow. True? So, and you have a magnetic field B which is perpendicular to that loop, but that field, B field is not a function of time. Which means, so the area which is defined by this loop, the B field है उसे perpendicular है, so you have that B field which is perpendicular to that area, but this B field is not changing with time, so ये वाला component जो है इस केस में आपके पास 0 है, so there is no changing magnetic field is constant. But what you have in this case is something else, and which is this component is not equal to 0, because when you are moving this thing, आपका loop का जो area है आपके पास increase होता है. And when that is changing, you have this component which is inducing an EMF in the coil, and that is generating a current. Okay? So how would you say it? आपका magnetic flux क्या होगा at a certain time? It would be given by जो magnetic field है जो कि constant है multiplied by the area of the loop, that would be length multiplied by this distance x. What would be the change in flux? That would be d by dt of d, l and x. Length is constant, d is constant, but x is something which is changing, so you can write as is equal to d l x by dt, and this is equal to what? This is b l multiplied by the velocity of the bar. Because with that velocity the x component is changing. So what would be the EMF which would be produced? The EMF which would produce is minus d by dt f by m. That is the EMF which would be produced inside this closed loop. And the main component here is coming because of the fact that the area जो है वो time के साथ change हो रहा है. It's not because of the change in magnetic field. So in this case you have just simply minus d l v bar. That is the amplitude of the magnetic field. That is the EMF which is induced in this wire, and because of this EMF you would have a current which would flow through this. If you have a resistor, आप current क्या होएगा आपके पास जो flow करेगा? That would be this EMF which is B L V bar divided by the resistor of the loop. That would be the current magnitude. So that's given by E by R. True? Is there any non-Coulombic electric field here? Non-Coulombic electric field कब produce होता है आपके पास? Whenever you have change in magnetic field, but there is no change in magnetic field, there is no non-Coulombic force, non-Coulombic field. It means that you have a Coulombic field which would be producing this current. और वो Coulombic field कहाँ से आती है? Any idea? This we studied in motional EMF. So what you have said, if this thing is moving at a certain velocity, यहाँ आपके पास electrons हैं जो negative charge हैं. Those negative charges are moving with a certain velocity in that direction, and because they are moving inside a magnetic field, a force is being applied on those negative charges. वो force किस direction में होएगा आपके पास? So you have V in that direction, B is into the board, so V cross B, it's the upward force, but because it's a negative charge, the force would be downward. So what you would have is negative charges which would accumulate on this side, and positive charges which would net accumulate on that side. So you have a potential which forms inside. लेकिन वो potential real charges की वजह से produce होता है. It doesn't produce due to a changing magnetic field. And because those charges can move, because they have a circuit to move around, so they can move and create current. And as long as you move it, the current would flow and you would have an EMF in the circuit.
Tell again how the charges are induced.
It's because of the magnetic force. So you have negative charges here, because they are the only free moving charges in there. if they are moving inside it, so if force is applied on them, they can move in this vertical direction. And when they move in the vertical direction, they can start a current inside it. So this is what motional EMF is. So motion EMF, it is produced due to magnetic forces and not due to non-Coulombic charges. Okay? But you can still explain it via Faraday's law. So Faraday's law can be due to changing magnetic field, it can also be due to changing currents. Changing area, not current. So this is a classification. This Ampere's law is quite a broad thing. It not only it contains a variety of different phenomena which you can explain with it, not only non-Coulombic force or non-Coulombic field. Similarly, we have another example. जिसमें हमारे पास क्या था कि let's say you have a coil जिसका length जो है बस A है, width इसका B है, and you have connected this coil with a certain, for example, with a certain motor. This motor can be a turbine in a dam, for example. So water falls on a turbine. The turbines, it moves, it rotates. And let's say you have connected this coil with that turbine. So this whole thing would rotate with a certain angular frequency, omega. And you have placed this inside a constant magnetic field. So let's say that magnetic field is in that direction. So you would have this coil which initially doesn't have any current, but you have connected it to a certain turbine, and because the turbine rotates, this rotates with a certain frequency omega. So what's happening there? Again, what you have is basically this thing, this component, because the field is not changing. The field is not changing with time. The field in which you have put it is constant. The only thing which is changing is the area of the loop. वो किस तरह change होता है? The area itself doesn't change, but the component of the area which is parallel to the beam, it changes with time as it rotates around. So, for example, आपके पास अगर ये loop जो है वो इस direction में है, so the loop is in this one, area of the loop is in that direction, which is the direction of the magnetic field as well. But after some time you is rotating, आपको क्या होगा? The loop would look something like this, with an area vector in this direction and the B field in that direction. The B field magnitude is still constant. The only thing which happens is that this gets rotated. It's rotating with time with a certain frequency omega. So let's say if that's the case, what would be the total flux in that case? Magnetic flux, इस केस में आपके पास जो होगा B magnitude multiplied by the area magnitude, and because both of them are parallel, so we will have this cos 0, which is 1. Okay? And what's the area? It is A multiplied by B, basically the length of each of the sides. Okay? What would be the flux in that case? A and B are perpendicular, so A dot B would give you a 0 there. Let's say that's the time, at time t equals to 0, that's the case, and this is the time later t equals to 0. So how can you write your magnetic flux? Is sort of a cos function. Because it's rotating, so it's a cos function. At time t equal to 0, it has maximum magnitude. At a later time, it's 0. Later again, it will become maximum again. So it's some kind of a cosine function. So you have B, AB multiplied by cos, and it's a cos of omega t because it's rotating with a certain increase of omega. So that would be your changing. That would be your flux, which would be time dependent. And this flux would be time dependent because area is changing, or the area which is facing to the magnetic field is changing, and not due to the changing magnetic field. So what would be the EMF which would be produced because of that? That would be minus d by dt of phi m. So that would be equal to minus cos sine plus, that would be B, AB, omega, that would be sine omega t. That's how the EMF along that wire would change. So if you connect a certain resistor to this, so the current which would flow in such a circuit, this would be given by this EMF which you produce divided by R. See? So that's how your generators work. And it produces a sinusoidal field and a sinusoidal EMF and a sinusoidal current as a result of this sinusoidal EMF. So that's what you get in your 60 Hertz outlets. Okay. Any question? So coming back to the Faraday's law in the normal sense in which the magnetic field was changing. So this morning we derived for a case जहाँ पे बस दो coils थे. You had a coil which was connected to a certain resistor, coil 1, that resistor 1, and then you had it connected to a certain potential or changing potential, and you have a current I1 which was a function of time flowing through this. And then you bring another coil in the vicinity of this. So it doesn't have any EMF of itself or a battery of itself, but it is close enough to this. So the distance between these two is Z, and the area, this has radius R1, this has radius R2. So if this current which is changing with time, if it is changing with time, it would induce an EMF on this side, and we said that the EMF which you induced in the second coil is given by minus and 1,2 multiplied by the rate of change of current I in the first circuit.
The current direction opposite is current.
क्या मतलब?
Coil 1 is.
इस sinusoidal है तो वो change होगा हर circuit के अंदर ही. ठीक है? So that's what we had. So R2. So one changing current which results in a changing magnetic field induces the current in another coil, and this is something which is called as mutual inductance. जहाँ पे M12 जो है is just a geometric factor, and it is given by the number of loops in each coil. So you have, let's say यहाँ पे N1 number of loops है और यहाँ पे आपके पास N2 number of loops है. So that will be the product of those loops multiplied by mu naught by 4 pi multiplied by pi R1 squared, which is the area of the first loop, the area of the second loop, divided by Z cube, where Z is the distance between the two loops. So it's just a geometric factor. It depends on the constant, it depends on the number of coils, and it depends on the area, and it depends on the distance between the two coils. That's what we did in this one. So N1 and N2 both would come into M12 itself. I guess this one was a bit confused. दोनों जो है वो एक ही M12 के अंदर. Okay. So just a bit of difference. These are coils which has n number of turns. What is the difference between a coil which has n number of turns and a solenoid which has n number of turns? So it's just, for example, if I have 5 coils, so I arrange them in such a way that they are something like this. There's a solenoid arrangement. So you have coils, 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 coils. But if you have something like this, for example, there is a coil, it's not a solenoid. Okay? So there's just a kind of basic difference between the two. Okay, so let's come to the next variant of the same problem. Let's say if you have a solenoid now, not a coil but a solenoid. Yes. And you have connected it to a certain battery whose potential can vary, and you have a resistance so that you have a certain current which goes through it. So let's say you have a certain constant potential V, so that a constant current I flows through it. If a constant current I flows through it, then the direction of the current would, inside the solenoid would tell you कि magnetic field जो इसके अंदर establish हुआ है किस direction के अंदर. So use your right hand rule, and the right hand rule would give you the direction of the magnetic field inside. Okay, so if the current is in this direction, the field is in this direction. What would be the magnetic flux through this loop itself? Magnetic field क्या होगी? That is given by mu naught. In the case of a solenoid, the field है inside the solenoid, it is given by mu naught n multiplied by I, where n is simply the total number of loops divided by the length of the solenoid multiplied by the current which flows through it. ठीक है? Let's say n जो है अगर total number of coils है in this distance d. ठीक? अगर करंट आपके पास कांस्टेंट है, B कांस्टेंट है, अगर B कांस्टेंट है तो जो फ्लक्स है वो आपके पास कांस्टेंट है, which will be given by mu naught n by d multiplied by current multiplied by the area, क्योंकि इसका क्रॉस, so let's say radius इसका a है, so that would be this multiplied by a squared, that would be the total flux which will be going through it. But this would be the flux which goes, so this is the field which is produced, but this is the flux which would pass through a single coil inside the solenoid. What you have is not a single coil in the solenoid, you have n number of solenoids, so the total flux होएगा through the whole solenoid phi m total. वो आपके पास क्या होएगा? That will be n times that thing, so that will be n multiplied by mu naught n by d I into pi a squared, that will be the total flux. ठीक है? क्योंकि यहाँ पे n क्यों है? क्योंकि जो फील्ड अंडर प्रोड्यूस होता है यहाँ पे वो सारे करंट्स की वजह से प्रोड्यूस होता है. इट्स नॉट बीइंग प्रोड्यूस्ड ड्यू टू वन करंट. ठीक? अब you have a magnetic field here, but you have also you have a coil as well. So you have a magnetic field which is passing through this coil, so you can calculate the flux which is passing through just one coil, which will be given by that thing. But you don't have just one coil, you have n number of coils, so you have to multiply it by n. So what you would have an n square in this expression. There's a total flux which is inside the solenoid, passing through a solenoid, magnetic flux. Now imagine if you want to increase the current. The potential आपका variable हो सकता है, so you have initially applied a constant potential, but then you start ramping up the potential. Current को क्या होएगा? Current would go up. So let's say the current, which is a function of time now, so it was initially constant, and you start ramping it up. Start ramping it up, तो क्या होएगा? B field जो है अंदर क्या increase होएगा? B field increase होएगा, आपका जो flux है through it would increase. अब flux increase होता है, so imagine you have these coils which are part of the solenoid itself. So what you are doing, you are increasing the field in this direction, which is out of the board. अगर वो field आपके पास increase होती है, तो flux इस direction में increase होता है, so you would have a non-coulombic field जो कि produce होगी, and non-coulombic field यहाँ भी produce होती है, solenoid के बाहर भी produce होती है, but more importantly, that non-coulombic field would also be produced at the position of the solenoid itself. ठीक? वो जब कभी मैग्नेटिक फील्ड चेंज होएगा, you would have a non-coulombic field जो कि produce होएगा, और वो सारे स्पेस के अंदर होएगा around that changing magnetic field and inside that as well. So वो यहाँ पे भी produce होएगा. So what does it tell you? That you would start having a field which would be in the opposite direction to what your field is doing. So your field is trying to increase its flux in this direction because of the changing current, but then you would have a non-coulombic electric field which would produce a flux in the opposite direction. क्योंकि B इस डायरेक्शन में है आपके पास, जब B इस डायरेक्शन में है, dB भी इस डायरेक्शन में है, क्योंकि फील्ड इंक्रीज हो रही है, तो माइनस dB by dt किस डायरेक्शन में होगा? वो इस डायरेक्शन में होगा। तो जो आपके पास सोलेनॉइड के अंदर आप एक EMF इंड्यूस करोगे वो अपोजिट डायरेक्शन में इंड्यूस करोगे। सो दिस इंड्यूस EMF का साइन इस तरह होगा कि दिस वुड बी द प्लस साइन एंड दिस वुड बी द माइनस साइन, नॉट द अदर वे अराउंड। ठीक है, सो दोस वुड बी द इंड्यूस्ड EMF व्हिच इज E, व्हिच इज द इंड्यूस्ड पार्ट। और वो किस वजह से होगा? दैट वुड बी बिकॉज ऑफ द रीजन कि आपके पास ये म्यू नॉट एन स्क्वायर्ड by d pi a squared di by dt। करंट आपके साथ चेंज हो रहा है टाइम के साथ, that's why you are inducing an EMF and then EMF has an opposite direction to the actual sense of the current. But if you are decreasing the current, then it would be in the direction of the magnetic field, so you can imagine you would have an increasing current. So if you try to ramp up, if you have a solenoid in a circuit and you try to ramp up the current, the solenoid would resist it. Then you try to decrease the flux back. That's what an induced EMF is doing. So you have kind of a, you can think of a certain resistive element in the circuit. It's kind of add a resistance to the circuit within the circuit. Any question? So, if there would be no induced EMF and you have a conductor, what would be the potential drop across a conductor? The potential drop across a conductor or anything is given by minus EL, basically, which is L is the length of the conductor. So in this case, L of the total solenoid and E would be the field inside. But because the field inside a solenoid, inside a metal, is within a circuit is so small, this drop is almost equal to 0, and we consider the only drop it occurs in the resistance inside a circuit. So जो wires के अंदर potential drop होता है, we don't consider normally because this is almost equal to 0. But now what you have is when you consider this induced EMF, you have added an extra potential across this solenoid, and you have extra potential across this solenoid. This dV across the solenoid, which is a conductor, is no longer 0, but rather it is equal to the induced EMF which you have induced inside the solenoid. You have a potential drop across it, just like you have a potential drop across a resistor. Make sense? Because you are inducing an EMF, so you have a potential drop in the opposite sense of the current.
तो जीरो किस केस में होगा फिर ये?
If you ignore, let's say, if you ignore there is any inductance in the system, basically क्या है? It's a conductor, कोई current flow कर रहा है, and चाहे conductor जितना भी लंबा होता जाए, जो potential drop across the conductor होता है, you can almost ignore it most of the time, क्योंकि conductor के अंदर जो E field होती है, this is so small that the total drop across it is almost 0. ठीक है? Or in other words, जो del V है, if you treat a conductor as a resistor, then इसकी जो resistance side is so small that the potential drop is small. So either way. Okay, so you have a potential. So what would be that potential? It would be equal to this thing, and this thing we can write as minus L di by dt induced, where this L is again a geometric factor and it depends on the geometry of the solenoid itself. It will tell you your potential drop across the solenoid and whether it is a small or whether it is big for a certain change in current. So this L, which is called as self-inductance, it is given by mu naught n, which is the number n squared divided by d, so the number of loop in the coil in the solenoid divided by the total length multiplied by the pi a squared, which is the area into this basically the self-inductance parameter of the solenoid, which is represented by capital L. So that circuit, now you can represent in a different way, that you have an EMF, which is your battery. Then you would have a solenoid, and then you have a resistor. Such that you have a potential across the battery, you have a potential drop across the solenoid, and you have a potential drop across the resistor, potential drop across the resistance IR. See? So you can assign your polarities. For example, you can assign any arbitrary polarity. So I'm going in this direction along the loop. So these are the polarities I assigned it. And then I can apply the loop rule on it, which is the total potential drop across the whole thing is 0, which is basically the conservation statement in energy or electric heat. So what's the total potential drop? So if, let's say I start from here and I move in this direction, so I have an increase in the EMF, which is the EMF of the battery. Then I have a potential drop across the solenoid. And so this solenoid, in this case, was an inductive. This is also called as an inductive element within a circuit. So there's an inductor normally less than an inductor. So I would call it the potential drop across the inductor minus the potential drop across the resistor. That would be equal to 0, or you can add plus, and then by the polarity you can assign it signs. So if I go in this direction plus, what would the potential drop here? That would be minus L di by dt, because that's what you have here. And what's the potential drop here? It will be current multiplied by R. That would be the loop equation for this circuit. So let's try to see how does this change. What sort of solution does it give you? Let's try to solve it. So what you have is N di by dt. This is equal to minus d by dt. This is equal to E minus IR, and you can rearrange it. So d I by E minus IR. This equals to okay, so that's your equation. And if I multiply L on either side, okay. So if I write, I can rewrite as di by IR minus E. This equals to minus 1 over L dt, and I can take R out from here, so I have minus I minus E by R, which is R, and this equals to minus 1 over L dt. To multiply R by either side, I have di by I minus E by R. This equals to minus R by L dt. So I have this part, no? I have the I term यहाँ पे and d term यहाँ पे. You can integrate it from 0 to a certain time t, and then you can say that this is an integral on current. You can assume that you started with a 0 current and you want to see at a later time what was the current at a certain later time. So let's say you start from 0 to t to a current I is your current integral. That would be at a later time t. So this would be the current at the time t. What would be this integral? It would, if you solve it, it would give you L of I at time t minus E by R divided by minus E by R, and this equals to minus R by L t. Okay, and that's after putting the limits. Take exponential on either side, what you get is I of t minus E by R. This time you have exponential e raised to power minus R T by L divided by minus E by R, which can multiply on either side. That would be your expression. I can rearrange it. The current you get is given by E by R minus, maybe just 1 minus E raised to power minus T divided by L by R. So I have rearranged this term somewhat. T को मैं ऊपर रहने दिया है, R को मैं नीचे लेके आया हूँ. So there's and there. So that would be the expression of the current as a function of time as you try to increase it through an inductor. So let's try to plot it. What does it give you?
Sir,
Yes.
Ln of I minus ER नहीं होना चाहिए, divided by minus E over R. DI over I हो गया ना सर, इंटीग्रल जो लिया था, तो डिवाइड बाय माइनस E over R क्यों हो रहा है?
क्योंकि आपके पास पहले आप ऊपर वाली लिमिट लगाते हो, what do you get is I of t minus E by R minus log of, फिर I आप 0 लगाते हो, log of minus E by R, दो log माइनस करते हो.
Sir,
Yes.
if you give us the direction बता दें कि वो opposite direction.
Doesn't matter. जो लूप इक्वेशन है, it would give you the correct sign. अगर उल्टा आता होगा, आपने उल्टा साइन किया होगा, लूप इक्वेशन would give you a negative sign anyway. So it doesn't matter. ठीक है? आप जौन सी भी वैल्यूज के साइन किया. So let's plot that expression current as a function of time. So what would be the current at t equals to 0? उसमें t is 0 करके देखेंगे, what do you get? You would have e to the power 0, e to the power 0 is 1, 1 minus 1 is 0. That's 0. What is the current for time, for infinite time? ये term क्या होगी आपके पास? That would be 0 because this is 1 over exponential to the power infinity. And with 0 we are left with 1, so that current will be E by R. So let's try to plot it. Let's say this is E by R. So you start with the current which is 0 at time t equals to, this is time of course. And then you have an exponential increase in the current until it reaches E by R at infinite time. And you can find out what's the time during which it falls by, let's say, that is the maximum current you have, which is I max equals to R. So if it falls by I max by E, which is that distance, so you would have this is equal to I max into 1 minus 1 over E. That would be the value of the current at this value. So that would give you a certain time, and that time is the time during which the current increases by a factor of 65%. And if you do it for that expression, the value you get is tau, this is equal to 1 over L by R, L by R. So in this much time the current increases by 65%. But the important thing here is that the current is not immediately going up, it goes up with a certain delay. So where does this delay come from? So you are trying to ramp up the current, and you are trying to ramp up the current, the inductance within the solenoid, it opposes that increase in current, so it slows it down and it increases it slowly rather than making it go up immediately. So instead of such a circuit, if I would have a simple circuit like this, and I would have ramped up the current, the voltage, so the current I would get is something like this. So I would immediately see an increase in the current and then it would stay there. We are doing it that way. So we are changing the potential in a linear way. That's why the current increase in linear. It's not due to some other phenomenon. Okay? So if you applied a certain potential, so अगर आपके पास simple resistor होता, the current would immediately shoot to the value, and that value would be simply I equals to V by R. In that case, V would be the potential which you are applying by the battery. But because you have inductor, the current increases slowly. And once the current increase there, it would stay there. So let's say इस सर्किट के अंदर आपके पास करंट इंड्यूस हो गया and a current I equals to E by R start flowing through it. What would you have as a result of this? यहाँ पे जो आप the battery had to consume some power to increase its current because the solenoid was opposing that increase in current. So the battery had to push harder to increase the current to that because the solenoid was opposing that. So, but once you get it, the current would flow with the same value. अब जो extra energy battery ने लगाई है, where does that energy goes into? So what you would have a current flowing through it, but on top of that current, you would have an electromagnetic field which would be inside the solenoid all the time, as long as the current flows through it and it doesn't change anymore. So you have established a current, but while you establish a current, in the initial phase of increasing the current, you have to work against the solenoid, and when you work against the induced EMF, that energy is stored inside this magnetic field within the circuit. The current flow will start where, and it is continuously going at a constant rate afterward, but you still have that energy stored inside the magnetic field within a solenoid or within an inductor.
Battery को ज़्यादा it is more difficult for the battery to increase the current in the start. तो शुरू में इसका gain भी ज़्यादा है.
Other thing. I mean, this is okay. So because initially the field is small, initially flux small है, तो change in flux small है, change in flux small है, so EMF weak है. जो opposing EMF है वो weak है.
अगर flux small है तो change in flux ज़्यादा नहीं होगा, क्योंकि low flux से high flux पे जाना है, तो बिल्कुल जैसे 1 से 10 पे जाने की उसके मुकाबले जैसे 7 से 10 पे जाना शुरू में तो ज़्यादा difference.
For example, if you have a flux to इस तरह change हो रहा है, for example, with time, and you have a flux which is changing like this, which would give you more EMF. Second one. I don't know if it makes sense, but yeah, that's what it is. That's a good question. So, the question is, what is the energy once the current starts flowing? What's the energy which you have stored inside this conductor or inductor, so to say? So first look at the power. What is a power which is consumed by a certain circuit element? That power is given by the current which flows through the circuit element multiplied by the potential drop across it. So if it is a resistor, the potential drop would be IR.
So what is the battery doing in statistics?
Sorry?
What the battery is doing work in the statistics.
Yes.
So what is it? Against what is it doing that?
Again, so you are trying to the battery was trying to establish a current in there. So you switch on the battery and it's trying to establish a current, but the moment it tried to increase the current, it was being opposed by this thing, by the inductance. So it was pushing the current back. So the battery has to work more to establish that current or to reach that current value which you want to reach.
So all the work that the battery does is stored in the inductor?
Is stored in the magnetic field as a result of it. So what would be the total power which you would have is the current multiplied by the potential drop across a certain element, and in this case the potential drop is the induced EMF which you have inside the inductor. So what would be the power then? The total energy during that time which it gives while the current increases from I equal to 0 to a certain current I, that will be given by the total power and multiplied by dt for a certain time 0 to t, because power is d omega dw by the work per unit time. So what is that thing? That would be I P induced dt from 0 to t, and that would be equal to I, what is that thing? This is L di by dt, and because work is energy, energy can't, like, energy is not negative, so I can ignore the sign of the EMF here. So that's what you have from 0 to t. So this cancels out, and what you have is inductance multiplied by I integral di from, in this case, then you would have a current which is the initial current minus the final current. Okay, that's what the total work, the energy which would be stored inside the solenoid. This energy which is stored is, then you integrate it. What is that integral? This is 1/2 L I squared, and the limit would be from I initial to I f. So let's say I initial is 0 and I f is I. That's what, let's say, we have. So अगर current flow कर रहा है I within the circuit, so the energy which is stored will be equal to 1/2 L I squared. What is L for the inductor? We already found out. It is equal to this thing for a solenoid. So let's try to find out, if you have a solenoid within the circuit, how much energy is stored inside a solenoid. This is given by mu L squared by d. Into pi a squared. What is the magnetic field inside? What is the magnetic field inside the solenoid? It is equal to mu naught n I, so that's equal to mu naught n by d into I. So you can write I as a function of equals to b multiplied by d, that mu naught n, and you have this is 1/2, this is inductance, and the current squared would be b d by mu naught n whole squared. So this you can write as 1/2, that would be equal to pi a squared d divided by mu naught multiplied by b squared. That would be the total energy what you have. And what is that thing inside the bracket? A is the radius of the solenoid and d is the length of the solenoid. So pi a squared d is the volume of it. So if I put this thing here, then if I divide it by the total volume of the solenoid, then it will be equal to 1/2 mu naught b squared. That's the energy per unit volume which is stored inside the magnetic field in a solenoid when a current I is flowing through it. So that is the magnetic energy density. So अगर आपके पास एक magnetic field है कहीं पे, and you know the magnitude of the magnetic field, and you want to know कि उस magnetic field के अंदर energy कितनी stored है per unit volume, this is the expression which would give you that thing. If you compare it with the energy of the electric field, what was it? That would be 1/2 epsilon naught E squared. So the total energy which is stored in an electric plus a magnetic field, or the electromagnetic field, is equal to 1/2 mu naught B squared plus 1/2 epsilon naught E squared. That's the expression for the total energy which is stored in any electromagnetic field. अगर दोनों field हैं आपके पास. Okay, you have a constant mu naught here and you have a constant epsilon naught there. What if you divided both of them by 1 and then you take a square root of those? What do you get? And what is that? Speed of light. These are constants. These are constants. ये दो constant है. This constant is related to the magnetic field, but this constant is related to the electric field. And if you divide those constants, take a square root, what you get is the speed of light.
Because it's an oscillating electromagnetic.
It's an oscillating electromagnetic field, and a magnetic field traveling the speed of light. So that's the speed of a wave, which is electromagnetic wave. This is something we have to study in the next lecture, next course, not lecture. But to get to that, what you have to do, you take Maxwell equation, you go to the differential form, you form a wave equation out of that, and you form a wave equation. From the wave equation, you get always the speed of the wave. The speed of the wave turns out to be 1 over v naught epsilon naught. सवा 6 स्टार्ट होता है. So let's look at another circuit in which I will include an inductor. So let's say I have a capacitor which is fully charged. Let's say I had a capacitor which I fully charged it, and once I fully charge it, I open the switch. There's no more current flowing in here. We have a conductor which is fully charged with a charge plus Q naught on this side and a charge minus Q naught on this side. What would be the current which would flow in this circuit now? So you can say, for example, this is negative side, this is positive side. You can start from here and you can make your loop equation. So I assign this a polarity of plus and assign this as a polarity of minus. Let's write the loop equation for this. What would be the potential drop across a capacitor? That would be given by Q over C. Okay? Let's say I am not taking Q naught here, I am taking Q, which is a charge at any later time t, for example, any German charge. And because you are moving in this direction, you have an increase in the potential, so I have a plus sign there. So when you move here, you have a decrease in the potential, so you have a minus sign there. And what is the potential drop across an inductor? That would be L di by dt, and that is equal to 0. That's the loop equation for such a circuit.
So, the arrow on the switch?
That's a switch, yeah. So first I recharge the capacitor and then I open the switch, and so that the current would flow in the other part of the circuit. Okay, what would be the current which, so let's say current start flowing in here. जब current flow होएगा, charge को क्या होएगा आपके पास? Charge will decrease. So I can write कि मेरे पास जो current है, that is given by minus dq by dt, where q is charged at any time. Okay? That's important, the minus sign, because if the current increases, a total charge decreases by that much amount. So that's the total current inside it, given in terms of the charge on the capacitor. So let me write this equation in terms of the charges only. This is minus L d by dt of current, where current is given by minus dq by dt, and that is equal to 0, so that's the total equation I get. Q by C, minus into minus is plus, and you have 2 times the derivative of charge, so you have d2q by dt squared, that is equal to 0. That's a sort of equation you should kind of familiar with. So let's rewrite this equation, d2q by dt squared, and I rewrite it in this way, this is equal to minus 1 over LC into, so there's a constant multiply by this. So you have second derivative of charge, which is, so charge is something which is changing with time. So Q is this, which is the charge on the capacitor, is a function of time. And so what you have is, so this is something which is called as an eigenvalue equation, where you have a second derivative of a function is equal to the same function multiplied by a certain constant. What would be the solution for this? That would be a cosine and sine, because that's what those, or e to the power I, which is again sine or cosine. And why is that the solution? You can easily see it. For example, I can write Q of t, your solution है मेरा, that is equal to Q naught e raised to power minus t by LC under root. That's the solution I have with the minus sign. That's that. Why is that the solution? Take the first derivative. What is the first derivative you have? You have I divided by LC under root into Q naught e raised to power I t by LC. So derivative exponential का क्या होता है? Exponential function multiply by derivative what's in there, and what's in there is I by LC under root. Take the derivative again. So you have again I or LC under root multiply होगा. So what you would have is I squared multiply by LC Q naught e raised to power I t by LC. What is I squared? This is a minus, and minus 1 over LC Q naught e raised to power I t by LC. And what is that thing? It is again my solution Q of t. So this is equal to minus 1 over LC Q again. That's exactly the same. Or you can have a real part of that equation. So you already know you can expand it into Q naught into cos t by LC plus I Q naught sine of t by LC. That you can make, expand it. क्योंकि e raised to power I theta क्या होता है आपके पास? It equals to cos theta plus I sin theta. And if you are interested in a real solution, you would take this part of the solution. So Q of t equals to Q naught cos t by LC, your root. That would be your solution as well. So either you take this one or you take that one, doesn't matter. दोनों को आप दो दफा इंटीग्रेट करोगे, you get exactly the same equation. क्योंकि यहाँ है. So what does that equation is? That solution. Whether, so let me take this as my solution and not that one, because you might not immediately see how do you plot that. But you can plot this one. Let's plot that one. So you have time, and this is charge on the capacitor. So what's the charge on the capacitor for time t equals to 0? That's, let's say, Q naught. And you have a cost function. So that's Q of t would change like this as a function. It's a cost function, so it would be a sinusoidal function. So you would have oscillation of charges and as a function of time. So you would have plus Q charge at one time and minus Q naught at another time. So what does it mean? That initially you started with this configuration, that this was plus Q naught, this was minus Q naught. After this much time, at this position, those polarity would change. This would become minus Q naught and this would become plus Q naught. And then again would change, plus Q naught, minus Q naught. So it would go back and forth, back and forth. What would happen to this inductor? लेट्स से जब फुली चार्ज होता है आपके पास, जब कैपेसिटर फुली चार्ज होएगा यहाँ पे करंट क्या होएगा आपके पास? 0. So let's try to plot the current as a function of time. That would be equal to minus dq by dt. We already have charge there. What is that? That is minus q naught. Minus sign का है, so that would be minus q naught divided by LC under root multiplied by sin t by LC. तो साइन फंक्शन होएगा, but with a plus sign. Okay, it's a plus sign. ठीक है, वो साइन का फंक्शन होएगा, लेकिन इसका एम्पलीट्यूड जो है वो थोड़ा सा आपके पास डिफरेंट होएगा, जो given by q naught by LC. ठीक है, just derivative there. So let's plot this thing now. जो कि current है आपके पास. So current is a sine function. So how would it look like? So it would start from here. So initially you have zero current because the capacitors are fully charged. But then you have a sine function. So the capacitor would get. So you would have maximum. You have maximum current when the charge becomes zero, and then you would have a negative current when again the charge becomes zero, and so on. So that's how. That would be the charge as a function of time, and that is current as a function of time. ठीक? So यहाँ पे आपके पास क्या है? T equal to 0. आपके पास charge capacitor fully charged है because it has a full charge on it. लेकिन current आपके पास क्या है? 0 है, which means that what is the energy inside the inductor? वो 0 है because the energy density inside the inductor is given by a total energy inside L I squared. अगर I 0 है आपके पास, इंडक्टर के अंदर जो वर्क या एनर्जी स्टोर्ड है वो 0 है आपके पास. So you have maximum energy inside the capacitor. So energy capacitor की क्या होती है आपके पास? Half Q C squared ये होती है आपके पास. So the charge is maximum. Q square और C होता है, sorry. Q square क्योंकि square इधर में होना चाहिए. जब चार्ज मैक्सिमम होएगा, जो एनर्जी कैपेसिटर के अंदर, so this is energy inside a inductor, this is energy inside a capacitor. The electric field नहीं है, these are energies. So इंडक्टर के अंदर एनर्जी मैक्सिमम तब होती है जब करंट मैक्सिमम हो, और कैपेसिटर के ऊपर एनर्जी मैक्सिमम तब स्टोर होती है जब आपके पास चार्ज मैक्सिमम हो. तो यहाँ पे आपके पास चार्ज मैक्सिमम है बट करंट 0 है, तो कैपेसिटर के ऊपर मैक्सिमम एनर्जी होगी, इंडक्टर के अंदर 0. Let's come at this point. Charge अगर क्या हुआ है? Charge becomes 0. Charge becomes 0, so all of the charge from the capacitor has gone. लेकिन you have the current now maximum. इसका मतलब है whole of energy is now in the conductor and not in the capacitor. When you come here, यहाँ पे again current is 0 now. करंट 0 है तो इंडक्टर में एनर्जी 0 है, बट चार्ज मैक्सिमम है, ऑल्दो इन द नेगेटिव डायरेक्शन. लेकिन यहाँ पे हमारे पास चार्ज का स्क्वायर्ड है, तो चार्ज का स्क्वायर्ड अगर नेगेटिव भी है वो प्लस हो जाएगा. सो अगेन एनर्जी इनसाइड द कैपेसिटर इज मैक्सिमम. सो व्हाट यू हैव इज दिस switch back and forth between energy between a conductor and insulator, and this circuit is called as a resonant circuit because this circuit oscillates with a certain frequency, and that oscillation is given by that frequency with which it oscillates is given by omega 1. This is the frequency with which the energy between the insulator and capacitor oscillates.
चार्ज के दो हमने देखा था सेशन में, एक इमेजिनरी और एक रियल. सर प्रैक्टिकली इमेजिनरी पार्ट जो है उसका किस चीज़ को रिप्रेजेंट कर रहा है?
It represents, it's a good question. It represents the phase delay between the current and the current and the potential. You would see like in the next. ठीक है, this is, so we represent phases, so for this you have to introduce phases of the field. Go on next. हाँ मैंने अपोजिट लेवल की आपकी बात सही है. ठीक है, that's